Alright, so this is the last video in our atomic atomic physics, our nuclear physics, and our quantum mechanics unit. It's the last video. So just a brief review. This is going to be over radioactivity, which most of you should have had in chemistry, so this should be a review for you. Just as a review for atomic notation, remember, as some examples, in order to figure out how many protons and the mass number and all that kind of stuff. The number at the top in this sort of notation is the atomic mass, which is your protons plus your neutrons. This notation at the bottom is this. Make sure it was in right focus mode. This number at the bottom is the atomic number, which is your number of protons. Another notation would be, say, Al26, and that's obviously your mass number. Okay, and so isotopes of the same element have the same number of protons, which is what defines the element as what it is, but different numbers of neutrons for a given element. So you could have, C13, C14, etc. Okay, enough of review. So radioactivity is the spontaneous emission of radiation from the nucleus of an atom due to nuclear instability. And after you get over a certain amount of neutrons, which you don't have to know, neutron to proton ratio, that's when the nucleus becomes unstable. So we're talking about the nuclei literally falling apart or emitting some sort of energy or emitting some sort of particle. So there's three main types: alpha, beta, gamma. Those are your symbols: little fish, little bee with a tail, and a little loop like that for gamma. So for alpha decay, this is when alpha particles are ejected from the nucleus. So when a nucleus undergoes alpha decay, it ejects an alpha particle. One alpha particle is just two protons and two neutrons, no electrons. Okay, so it's basically a helium nucleus. Okay, a helium nucleus. So a helium nucleus is an alpha particle, and that's what gets ejected from your nucleus when it undergoes this sort of decay. Okay, these have a 2+ charge, obviously because they don't have they have two protons but no electrons in this type of particle. Okay, and this is the weakest type of radiation when these are emitted, and it can be stopped by a sheet of paper. Sheet of paper. Okay, so the weakest type of radiation can be stopped by a sheet of paper. So I just want to show you a nuclear equation example. Okay, so if we have uranium-238, okay, and it undergoes alpha decay, then what you're basically releasing, an alpha particle is being ejected from the nucleus. So what you have left is an atom that has 4 less for the atomic number, so it's going to go down to 230. I'm sorry, the atomic mass, and 2 less for your atomic number. So 4 less for atomic mass, 2 less for atomic numbers. These have to add up to equal these. Okay, and then just look on the periodic table to see which 190 is, and that's going to be thorium. Okay, and on the AP exam, they'll give you that information. Like, you won't have to memorize, obviously, the periodic table or anything like that. Okay, all right, so for beta decay, it's actually 2 types, and I don't know about who taught you chemistry, but when I've taught this stuff before, we only talk about one type, so one of these types might be new to you. So with beta decay, there's 2 types: electron and positron emission. So electron emission and positron emission are the 2 types, and both of these can be stopped with your hand. Okay, so it's kind of the intermediate range of energy. So alpha is the weakest, gamma is the most, beta is in the middle. So for electron emission, which is also known as beta negative decay, that's how I'm going to refer to it as, beta negative, which is also denoted with a little beta sign with a little negative. It's when a neutron decays into a proton, an electron, and an anti-neutrino. Okay, so think of it this way. You have a neutron, it decays into a proton, and the electron gets ejected, and the antineutrino. This is just another type of particle with very, 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 very minimal mass. You don't really have to know a lot about its properties. Just it's like a little curvy V. It's like a straight line and like a little curve for a V. Draw it again, like that, with a little line over it. That's an antineutrino. So these two get ejected. This guy, that proton stays in the nucleus. Okay, so if your neutron is decaying, that means your nucleus loses a neutron, but it gains a proton. So what happens to your atomic mass? It stays the same. Okay, if you lose a neutron, gain a proton, your atomic mass doesn't change, but your atomic number does what? Your atomic number is your number of protons. So if you gain a proton, your atomic number goes up by 1. So beta negative decay is actually the only type of radioactive decay in which you actually move up on the periodic table. Okay, you move up on the periodic table. So neutron decays into a proton and an electron. This electron is also known as a beta particle. Beta negative particle. That's what's getting stopped by the hand. You know, if I shot you with the beta negative decay gun, I'd be shooting basically electrons at you and antineutrinos at you. Okay. All right. So let's see. Let me give you an example. So if I have, once again, uranium-238. Okay. If it undergoes beta negative decay, then remember we said that your atomic number doesn't change because your neutron's decaying into a proton and an electron. Your atomic number is going to go up by 1 because you're gaining a proton. Okay? And number 93 on the periodic table, if you look, is neptunium. And you're going to have an electron with that's ejected, and an antineutrino. Okay? All right, that's beta negative decay. Beta positive decay is when a proton decays into a neutron, a positron, and a neutrino. So this is when a proton decays into a neutron, a positron, that's going to get ejected. Guys, a positron has the same mass as an electron, but is positively charged. So mass of electron, but it's positively charged. Okay, and you denote it with a little e with a plus 1 on the bottom, like that. Okay, and a neutrino. That was an error. It's just a little v with no line over it. Okay, so the proton decays into a neutron. So what happens to the atomic mass? It stays the same. Okay, so atomic mass stays the same. I'll write that for both. For both of these types of beta decay. Atomic mass stays the same. Remember, for beta negative decay, the atomic number went up by 1. Up. For this one, if you're losing a proton, your atomic number is going to go down by 1. Goes down by 1. Okay. All right, let me give you an example. We've got, let's use uranium-238 again, just as our example. If it undergoes beta positive decay, then remember atomic mass is going to stay the same, but the atomic number is going to go down by 1. Okay, and that's going to emit a positron, oops, and a neutrino. Okay. All right, gamma decay is the third type of radioactive radiation. It's basically pure energy. So electromagnetic radiation, or gamma rays, that are given off when an excited nucleus falls to a lower energy state. gamma decay almost always only occurs after another decay process. So for example, if an alpha decay occurred within a nucleus, then gamma decay, that makes that nucleus excited, and so then gamma decay would happen almost immediately after. We're talking 10 to the minus 20th seconds afterwards. So it almost always occurs after another nuclear decay process. So basically, this is the most penetrating form of radiation, and it can basically be stopped by several inches of lead. Okay. And the good thing about this is that nothing about the particle number changes. So if we have uranium-238 and then it undergoes gamma decay, you denote an excited nucleus by putting a little star next to it. So you've got your star here, and when you show it decaying, nothing about the atomic number or the atomic mass changes, and you just show that energy was released, which you can either write the word energy or sometimes you can just put a little gamma sign to show that gamma rays were released. So in terms of decay rules, for general rules, when one element changes to another through decay, this is called transmutation. And the sum of the mass numbers must be the same on both sides when you're looking at a nuclear reaction. When you're looking at that nuclear reaction. So for example, here we had for our beta negative decay, our atomic number was increasing by 1. So if you do 93 minus 1, that's going to be equal to 92. Okay. The sum of the atomic numbers, if you flip the page, the sum of the atomic numbers also must be the same on both sides so that we don't violate any laws of conservation, because the conservation laws hold for energy, mass, and momentum. So for nuclear reactions, you can have nuclear reactions, meaning you can have atoms that either bombard each other or they get split, and that's fission or fusion, without a specific type of radiation being released, like alpha, beta, or gamma, and these are called nuclear reactions. So the structure of nuclei can change when you bombard them with particles or energy, and becomes filling in the blank. This is kind of, so for example, if you had a helium atom that you bombarded a nitrogen atom with, and I want to know, well, what are the products going to be? And let's say that I know that one helium atom is released. It becomes a matter of just adding it up. So we know that the total number for the atomic mass on the reactant side has to equal the total number on the product side. So we know that this product has to have an atomic mass of 18, 4 plus 14. Okay, and it has to have an atomic number. 2 plus 7 is 9, and we have this 1 here, so this has to be an 8, because 8 plus 1 is 9. So we're dealing with oxygen. So it must be oxygen in this example. Okay. So fission is another type of nuclear reaction. It's when a nucleus of large mass, pretty much greater than iron, iron's kind of your valley of stability right there, when a nucleus of large mass greater than iron splits into 2 smaller nuclei. Okay, so an example of fission is usually you end up bombarding the nucleus first to give it energy. Usually you bombard it with a neutron. So let's say we had uranium-238 and we're bombarding it with a neutron. Okay, this is going to cause that uranium to split. So you're shooting that uranium with a neutron. This is going to cause the uranium to split, in this case, in this example, into barium and krypton and 3 neutrons. Okay, 3 neutrons. So a chain reaction occurs when those free neutrons here basically trigger fission in other nuclei in the sample. And so it's kind of like a chain reaction. Okay, and this is how atomic bombs work, or some of them work. So that's fission. Fusion, is when two light nuclei, basically atomic mass less than iron, fuse to form a heavier nucleus. Okay, so for example, if we had tritium, actually I thought trillium, it's helium-3, plus helium-3, add those together, it's going to form helium-4 plus 2 hydrogens. That's an example of fission. Or excuse me, a fusion. Okay? Just remember that large amounts of energy are released with both types of reactions. Okay? So whenever you undergo fission, energy is also released. Should probably put energy over here. And then anytime you undergo fusion, energy is released as well. So a small amount of mass is lost, very, very small amount. Okay, not enough to affect the atomic number, so that wouldn't change here. But when large nuclei split and when small nuclei fuse, equals delta mc squared tells us that even a small amount of mass converts into a very large amount of energy. Okay, so here's some kind of nuclear reaction examples. Nitrogen bombards uranium. That forms uranium-236. Okay. And so what ends up happening is that decays into cesium, some unknown element, and 3 neutrons. So this is basically the reaction that we're trying to balance here. So we've got 3 neutrons. So that's 3 up here at the top. 3 plus 141, that's 144 on the reactant side. 236 over here. You're just going to subtract those, and you get 92 at the top, because basically that 141 plus 92 plus 3, okay, has to equal 236. And then that's 0. So 55 plus blank has to equal 92. Okay, so that's going to be 37. And if you look at the periodic table, that's rubidium. Okay. So what process is this undergoing? Well, this is undergoing fission, because you're splitting that large nucleus. Okay. Here we have radon, and what particle do we have here? It's an alpha particle, so we're undergoing alpha decay in this one. Okay, so 222 minus 4, that's 218 at the top. 86 minus 2, that's 84 at the bottom, which gives us polonium. Okay. And here we have iodine. Okay. Now, the atomic mass is staying the same, but the atomic number is going up by 1. That's a certain type of beta decay. Okay. So that's going to be beta negative decay, also known as electron emission decay. Okay. So what's going to be produced is an electron, because remember that proton, that neutron you're losing, that neutron decays into a proton and electron plus your antineutrino. Okay. All right, quick on half-life. Half-life, you're not really going to have to calculate using the formal half-life equation. Just kind of conceptually, you'll have to kind of manipulate questions conceptually with half-life. So the half-life of a substance is the amount of time it takes for half of that sample, half of that substance to decay, to radioactively decay. So here's an example. If I have iodine 131, it has a half-life of 10 days. Okay. If I have a 100-gram sample, how much is left after 10 days? Well, half as much. So after our first half-life, after 10 days, I'll have half as much. I started out at time 0 with 100 grams. Okay. What about after another half-life, after another 10 days, after a total of 20 days has gone by? Well, basically when we say that half of it decayed, that means that means I have 50 grams of the iodine 131 still left, and then 50 grams has decayed into something else. We don't know in this example what that is, but decayed into something else. Okay, so after another half-life, I have 25 grams left. After another half-life, a total of 30 days, I have half of that left. After another half-life, Fourth half-life, I have half of that left. You guys get the idea. Okay.